We covered so far only the rotation matrices. Now let us speak about the general motion. So in general motion, everything will be almost the same, but we can think like those two frames, the origin of them is not the same, but there is a bias between them. And in this case, we use homogeneous transformation matrix that that has also a position vector. The homogeneous transformation matrix equal to the R0 P1. So it will be 3 by 3. It is the vector of 3 elements. So the result, this matrix will be 4 by 4. So here I have several slides about how can we derive it. And the idea is that P A equal to R A B P B plus some bias B. And it will be nothing else than this P actually. So here there is a derivation, but I do not want to spend time on this because it's pretty obvious. If you do interested in the details, I encourage you to take a look at the Kevin Lynch book. So before, right here, for the P, we had X, Y, and Z. But now we're going to use a capital P instead of just small p. And it will be X, Y, Z, and 1, since H is a 4 by 4 matrix, and in order to do the calculation, we need an extra 1 here. The notation will be pretty much the same. For example, we have a representation in a frame, for example, A. If we multiply it with the HAB, we will be left with the PB. And using this homogeneous transformation matrix, we can go from one frame to another, or we can rewrite it in a way PA equal to HAB PB, and HAB will be equal to the HBA inverse. Right now, the inverse will not be the H transpose. The equation will be like this. Also, the H is also a group. It satisfies the axioms to be a group with the operation of multiplication. So here also you have a closure, associativity, identity, and inverse elements. And H could be used in order to represent a position and orientation of a body, and also in order to express the change of orientation and position, to express the motion. So after the moment when we derived the rotation matrix, then we did this kind of multiplication in order to derive the angular velocity. Right here we can do the same thing actually. And what can we derive? So let's assume that we have PB. So let me just continue the something that I already wrote. So PB equal to HAB times PA. And let me put a derivative sign right here. And let us do the multiplication. So it will be HAB PA. I also could write HAB PA dot, but PA dot also will be 0 because we talk about rigid body. The same thing can be used for elastic body, but P dot will not be 0. It will be something else. We can write an expression for PA, and we will be left with HAB PB. So the notation is pretty close to the something that we had for the angular velocity. And this is called a twist. And twist is the something that expressed spatial velocity. And it's not in skew symmetric form, but in matrix form. So it will be denoted by the T, like twist, and just like we had for the angular velocity, it will be a twist of A that rotates around B, and the motion is expressed in what frame? B. So this is the twist of body A that moves along around in respect of a body with a frame B, and the motion expressed in the frame B. It's like a body A moves around space, B like space, and the motion expressed in the space frame. But also we can write the same motion of A that moves in respect of B, and we can express this motion in the frame A. And it will be just A here, B will be here. Where should I put a dot? Right here. If you do the multiplication 4 by 4 times 4 by 4 matrix, you will be left with also another matrix 4 by 4. And it will look like this. So you will have an angular velocity in skew symmetric form and linear velocity. But be very caution with this velocity. It's not something that is. It's not. It's some kind, another kind of velocity. It's not really. It's not really a real velocity.
You can say that's the velocity of the origin of this.
It's a velocity of a body. It's not an original frame, but it's something else. I need to explain you with another terms, with another structures, but we can rewrite this twist in a vector form, and it will be components for the actually for the angular velocity and the linear velocity, but this is not the projection for the x, y, and z. It's not like x dot, y dot, and z dot, something that we already know. It will be a little bit different from it. I need to explain you the all materials. We're gonna use it to calculate the actual velocity, but it's something a little bit different. Actually, the third practice task is needed to identify the difference between this twist and actual velocity. So this homogeneous transformation matrix is, if the homogeneous transformation matrix is a differential function of time, it could be shown that the product is belong to something which is called Lie algebra, SE3. So SE3 is this space, but not for the R as the manifold, but as a H as a manifold. Here, if we'll do the transformation into the vector, actually, it will be like 3 entities for the angular velocity, 3 entities for the something which is called like linear velocity, and we will have 6 numbers in the column, right? And actually, it's a way how can we represent a motion in in 3D space when we, by definition, has we have 6 degrees of freedom. We can use this way of representation, and if we'll do this, we'll have n parameters and n numbers. Like they will be equal to each other. So I have done this. Look, P dot, P capital, capital P dot. If we will do the time derivative, you will see that P dot equal to the x dot, y dot, z dot, 0, right? Do you agree? And actually, there's something that we used to is this. So P dot equal to twist times P. So let me just write P dot equal to, and I will skip all the indices. T in this matrix representation, P. So P dot will be the velocity that we familiar with. It will be the twist, and this will be the position that tells us where is the frame or a point that we are interested in. It's just like we had this example with the one link, right? So we can calculate the linear velocity right here. It will be angular velocity times the lever, right? So here v will be angular velocity times L. But right here, it will be also angular velocity times L over 2. So the v will be different. In order to calculate v, we need L. We need to know where is the point that we want to calculate. And this is your L. And twist actually is something that will be constant for all the frames of the body. So angular velocity times p could be rewritten as the vector omega vector product p by the definition of skew-symmetric representation, plus some initial value of the velocity. So this is like the form that we're familiar with, right? Here we know that the velocity equal to the angular velocity times L, and it's just something that we have right here. So twist could be write it in a vector form right here. And when you see the tilde, it means that the matrix in the twist in a matrix form. If there is no tilde, it means that the twist in a vector form. So vector form, matrix form. And you can express it in a body frame or in space frame that we just did it right here. Or we can also express it in some arbitrary frame C, for example.